So I got to say, it's a real pleasure to be with you guys here today. I have to say something personal. This meeting combines some physics adventures that I've undertaken, spaced by 45 years apart. And it's a delight to bring these two things together, actually for the first time in a few days. And so I'm going to quickly, Morgan gave you a little bit of outline of what LSST is about. I'm going to quickly go through a bit of that, but pause more and focus on things that are really relevant to the target of opportunity, opportunities with LIGO, and et cetera. So first thing you do is you get together a bunch of people that are really good technically, and you try to build something. And so this was a number of years ago, but we now have our team that is building LSST is now 187 strong, so that's more than these. It's we're budget capped and schedule capped, and we are in construction, so it's a very different atmosphere than it was during the R&D phase. And so that's what it's going to look like. It actually looks almost like that now, except for this part. We're going to put this on next month. But in just a single sentence, it's an optical near IR survey of half the sky, covering 300 nanometers to 1.1 micron to 27.5 magnitudes. That's a couple of microjanskis, based on roughly 900 visits to each patch of the sky over a 10-year period. And it's, we're going to, well, I'll explain more about that. But if you want to read more about the scientific capabilities, this looks like it's an old archive paper, but we keep it up to date. So the last update was in 2015. Anyway, you can go to this telephone number and find out a lot more about its scientific capabilities, driven by a lot of science. And so this is our optics. We are not using modified gravity to hold this whole telescope together. And so the light comes down, reflects off of the annular primary, off the secondary, off the tertiary, and then into the three refractive elements in the camera into a focal plane, which is the largest camera. It's going to be my last camera. It's huge. It's many gigapixels. And the mirror, thanks to Charles Simoni and Bill Gates, is now finished. This is an earlier phase a couple of years ago. It is now in storage in a hangar in Tucson, awaiting to be shipped down to Chile after one final check. And it's a funny kind of mirror, as I showed you. You can see the outer part of it, which is the primary. Up there somewhere is the secondary. It's a separate thing. It's under construction right now. And then this is the deep dish tertiary F1 tertiary mirror, creating an F1.2 beam into the camera. And why do this? Well, you need more than one, and you need more than two mirrors in order to get a very wide, rich field. It's just an optical fact. So we have 6 aspherical surfaces, and we have 6 chances to get it right. And therefore, we can get exquisite imaging over a wide, roughly 10-degree field. The camera is an adventure of its own. This is a 3.2 billion pixel camera. It's big. It's about the size and weight of an SUV. And it's, you can see here by this sketch, it's about 1.6 meters entrance aperture. And you can just make out the focal plane, which is a bunch of CCDs. I'll give you a picture of it in a second. There's only one trouble with this camera. As you might imagine, looking at that previous picture of how the thing is all put together, it sits in the middle of the beam of the light. It sits in the middle of the light beam that comes down from the sky and goes up to the secondary and back down to the tertiary. It sits in the middle of that. So there's no room to put stuff that I'm used to putting stuff around, like filter slides, electronics outside. No, everything inside the camera, including all the filters. And so it's an interesting mathematical theorem that you can get only a maximum of 5 discs inside of a cylinder that are 0.7 the size of the cylinder. It's an exercise for the student. Anyway, only at one point, at any one point in time, we have a maximum of 5 filters we can have in there. But as I'll show you in a minute, we're going to have 6 of them. So we change it out. So this is a huge undertaking. It's dissipating at 10 kilowatts. We have to take all that heat out and put it somewhere else in the mountain, so the outside surface is the same as the nighttime temperature. So it's a big undertaking. The Department of Energy is funding this. Price is $165 million, and the rest of the project is the NSF. I threatened to show this to you. Yes.
Sorry, since you mentioned the sort of unusual geometry of where you put the filters, could you show on this picture where they get stowed?
You see this puppy?
Oh.
That's a filter. And if you want to instruct it to move down in front, there's this little assembly here. These rails guide the filter in its motion down in front of the camera. There's a video that's well worth watching on our website. It's a little scary. It takes a total of 90 seconds minimum. It's probably going to be more like 2 minutes to change filters.
Are all of them exchangeable?
Except for the 6th, which is not in here. So there's a little port where we have to bring the thing down horizontal, rotate the camera to a certain attitude, and then there's a port somebody can go in to take out a filter and then put another one in. So we're going to put...
oh, I see. They're arranged in a ring.
Yeah. So here's another one.
Okay.
There's another one over there. Yeah, there's five of these puppies in here. And so this is our 6 filter bands going from the ultraviolet to the near infrared. And it's this filter that often is not in the camera, the ultraviolet filter. We will put it in for campaigns. And I heard during this conference already that it would be awfully nice to be able to have a campaign looking for U-band transients. But frankly, the G filter is pretty sensitive also in the reddish, the bluish part of the spectrum. And this will always be in the camera, except when we put the U filter in. So we'll take the Y out, put the U in. Anyway, this is including atmospheric absorption. This is our 6 filter system. And from this, we can get a 4-person's spectroscopy of galaxies and get photometric redshifts. And very good photometry. We have requirements of 0.5% or better. So this is the layout of the focal plane. There are 189 4K by 4K pixel CCDs, and they come in rafts of 9 CCDs, 3 by 3 arrays. And each raft has in it, behind the CCDs, all of the electronics. So I normally put electronics outside of the Dewar. Why would I ever put electronics in the Dewar? But we don't have that luxury. Everything has to be inside the Dewar except for the graduate student. Anyway, so the point is that all of the electronics is in the Dewar, and we come out with optical fibers. So the data is digital on the output. A little bit scary. We're actually building these things now. We have several of these built, so that's the state. 2-second readout. That was hard. I got it down to 2-second readout. I designed the project to have a 2-second readout because I wanted to have very short exposures. And so the idea was to have something on the order of 10 to 15-second exposures, and if you have more than a couple seconds readout, you're wasting time. This is being pushed hard at. It might end up being 2.5 or something, but we're going to get pretty darn close to 2. Data transport is an exciting issue. We're up on top of a mountain in northern Chile, and there are pairs of optical fibers going in different directions up to Illinois. We have a computing center at NCSA, headquarters site in Tucson. We have a data site, a base facility down in La Serena in Chile, and then a French processing center that is going to reduce in Lyon, is going to reduce half of the data. It's a big data reduction issue. The data management costs are huge. They're going to be the dominant cost in operations. A little bit more about data management. We are going to have about 15 terabytes of raw data every night. We will acquire about 500 petabytes of sky data plus calibration, dome and et cetera, calibration data over 10 years. All of that's going to be on spinning disk. And then they'll, this doesn't mention it, but in order to do science with something like this, you actually have to do very large simulations. And that's going to dwarf this 500 petabytes. It's going to be about 5 times as much data from the simulations. So it's a lot of data. When I give a talk at Google and talk about this, they yawn. But when I tell them what we want to do with it, they start getting excited. Because they don't normally, yeah.
So 500 petabytes is going to be the data storage for the next generation of Titan.
Say again?
500 petabytes will be the storage for the next generation of Titan. The question is, where are you going to store the data?
On spinning disk.
And you have already...
We have a plan. We're not buying it this afternoon. Anyway, so there's a lot of stuff you might imagine that you have to do with the data. You also have to continuously monitor the quality of the data. How do you know you don't have a transient object, or maybe it's some kind of funny problem with amplifier 157? There are all sorts of quality control issues. We have to know quite a lot about the point spread function. Every day we calibrate the telescope by scanning a laser across that entire frequency range and mapping out the response of every single pixel every day. So it's a big data management challenge. And then we have a special database that puts time and space computation close. It's a higher dimensional database so that you can do all sorts of cross correlations in a fast way. And as I mentioned, we have now several hundred gigabit per second fibers. This was last week. It probably looks different. I didn't bother to look. So this is the construction site near Cerro Tololo. If any of you guys have been down to Cerro Tololo, it's a day's walk from there. You might imagine, you might ask, what is this thing? It turns out, well, we're looking at the sky with LSST. It's also incumbent upon us to actually know what the absorption is along that line of sight. And so this telescope, called the calibration telescope, is going to have a spectrograph on it. It's going to look at a hot blue star in the field as we're observing that field. And thanks to the atmospheric science community, there's a program that inverts that spectrum to give us the absorption, even the gray term in the absorption, certainly. So this is coming along. We're just a couple of years, actually only 1 year away from getting this finished. And so this is our integrated schedule. Very quickly, there are 3 major departments in this project: the data management, telescope construction, and camera. And this is sort of a high-level Gantt chart. So the magic day occurred in August 2014 when we got the go-ahead from the National Science Board to begin construction. That was long anticipated. We had effectively the go-ahead from the Decadal Survey in 2010. It took a while. And so we started spending serious money at this point. And so the camera construction is currently the pacing item. It's taking us a while. Details. Anyway, we hope to be able to ship it to the summit around about 2020, late summer, and then go through commissioning phase, starting up observations in 2022. But there's a lot we can do before that, because you saw the state of the construction. The telescope and everything will be ready to go inside of a year. So we're building something called the ComCam. And so one of the first things that we're doing, in addition to putting the telescope and the dome together and all the labs, we're building one of those single racks, one of those 3x3 CCD racks, and we're going to put it on the telescope as a as a proxy for the LSST camera. There's a lot we're going to be able to learn from that experience, and that will be put on the camera only a couple of years from now. Sorry, that'll be put on the telescope only a few years from now. So we're actually pretty close to first engineering life. A couple of years. We're going to learn a lot from ComCam, partly because there's a lot of software development going on, and we're going to validate a lot of those algorithms using ComCam rather than wait until we have the main camera on and say, oops. And so there's a lot of feedback from the data management department along the way here towards commissioning. There'll be a science verification stage once we have the main camera on, where we'll actually go through, and we allowed ourselves a little bit of time, as you can see, for a shakedown cruise to make sure that everything is working well and that we are able to deliver what we promised. And the viewer is almost ready to come down. So this gives you a picture on the sky of how we're going to paint the sky. And this blue area is the Wide Deep survey. It's about 18 to 20,000 square degrees. It goes all the way from about a couple, plus a couple of degrees all the way down. We're going to cover these other areas, sort of colored yellow, less intensely, but we're going to cover them. And we're going to look at transients in this whole area. This is a mistake. We're not going to do that, but we're going to do that. This is an issue having to do with the current state of our operation simulation software. We'll cover the galaxy. We're going to I'll give you an example project that we're going to do for that. Yeah.
It's hard to tell from the color scheme. What's the intended number of exposures in the galactic plane?
Yeah, it is hard to tell. It's sort of greenish, right around 100 and around 200.
Okay.
Revisits to every single place in the galactic plane, and it is up to the community to tell us what you would like us to do, because the cadence has not been set at all. We have example cadences, and I'll give you an example of one, but the scientific community is going to have to decide what we're going to do. You see these little tiny circles? They're darker blue. These are deep drilling fields, and I'll tell you more about them in a minute. That's another mode of observing. This is a service to humanity. Currently, NASA is not paying us anything for this service. Maybe they will eventually. But it is to discover all the Earth-threatening, as many as the Earth-threatening asteroids as we can, by looking into twilight, morning and evening twilight. And this is high air mass, so it's pretty useless for a lot of the other astronomy, except for some transient work. And we're going to cover around 5,000 square degrees of sky every night. And there are two modes of that. We've only simulated one of them, but one mode is sort of the standard cadence that we're using currently in our current operation simulator. But another one is you instead of covering this much area every night, work on half of that area. But then as the month rolls on, you move that so that at the end of the year you've still covered as much sky as you were going to originally. What that tends to do is to increase the rate at which we return to the field, which is of interest to this community. It would double our revisit rate, and that's probably good. I'm pretty sure that's going to happen, and that's called a rolling cadence.
So you're saying that in any case, 5,000 square degrees would be covered in a night, but it's a question of whether you...
No,
you're saying,
no, you would cover a different amount of area every night. So you can say divide the area that you're covering during that night by 2,
Yeah.
which means that then you can go back to each
Okay.
piece of the sky twice as often.
Okay.
Compared to other facilities, this is probably one of the reasons the 2000 decadal survey thought this was pretty good. This is a huge increase. This is a log plot in terms of étendue or throughput. Just to remind you, the amount of data that you get out of a survey is proportional to the product of the étendue, which is itself a product of the number of square meters of collecting area times the number of square degrees in the snapshot, times the amount of time that you're on the sky. And so there are a lot of facilities here, and you see these black bars are the imaging part of the survey to be compared directly with LSST. The reason why some of these bars have a little white thing on them is because those telescopes were not used by imaging during that period of time. They were used in spectroscopy mode. So anyway, it's a huge advance, and you know, when I was designing this thing way back in the 90s, it was you know, you got to this stage where you realize that this is in principle possible. And then when you realize it's possible, all sorts of things come to mind. Mainly, you can do everybody's survey. You don't have to keep doing that guy's survey with those parameters followed by that guy's survey with their parameters, etc. You can do everybody's astronomy pretty much at the same time. And it's really a transient detection beast, which is really fun because we can take really short exposures. But I will get to this in a second. If you people care about how rapidly we cover the sky, how rapidly we can, how many points we can get on a light curve per unit time, if you care about that, you should let us know, because we're not hearing a lot from the scientific community about timescales less than a few hours. We're just not hearing anything. So here in words or in real numbers is the deal. There's this main so-called wide, fast, deep survey of at least 18,000, more like 20,000 square degrees to a uniform depth given by these numbers. These are 5 sigma depths. So space telescope type depth. And then there are about 10% of the time, actually maybe a little less now, somewhere around 10% of the time, we are going to go and do a different kind of survey, ultra deep. So there are going to be up to 20 selected fields, maybe 15, which is a lot of square degrees, and we're going to cover them in a movie mode. So during every night, we're going to spend roughly an hour during the night taking continuous exposures, not moving the telescope, just in the 10 square degree field of view of the camera, just in the movie mode. And that will discover a whole lot of transients on the time scale of 15 seconds. So that's an interesting mode actually for this community. And then, even more interesting for this community is that, so we're going to cover this area of the sky with, the baseline is pairs of 15-second exposures. Go to some place in the sky and take an exposure for 15 seconds and read out. It takes about 2 seconds to read out. And then we're going to take another one and read that out. And then it takes about 5 to 7 seconds to slew the telescope to the next field. So it's pairs of 15-second exposures. So it's basically 30-second visits to every piece of the sky. And then we'll come back to that same piece of the sky in an hour, or maybe if we have rolling cadence in a half hour. And we just continue this night after night all year for 10 years. But there's other things you can do, and the community has come up with a fairly long list of other cool things to do with the remaining 1 or 2% of the time. And that's where I think that the target of opportunity mode fits very nicely. That's still a lot of nights. And but here's the data management problem. As soon as we detect a transient object or a moving object, we are going to release all of that information to the world within 60 seconds of detection. So we allow ourselves a maximum of 1 minute to do all of that computation. It turns out to be a pretty big, tall order, but we think we can do that. And that will feed, that will be the input to the further downstream classification of objects that are of interest to us here in this room.
Can I ask a philosophical question?
Yeah.
So, with this rapid analysis and alerts on transient objects, are there transients that you would find in the LSST data within 60 seconds, I mean quickly, that you would identify as something that you would want more exposures on? I mean, you know,
Yeah. So that's
just
a good
based on the
question.
LSST
Yeah.
data alone.
And so the nice thing about the survey is that you will get more exposures of it.
I know, but I'm saying, is there anything that you'd find that you would want to then, you know, modify the survey just on the basis
So if there's
of-
a single object in, say, the 10 square degree field, by the way, there are 200,000 galaxies in each exposure and about 20,000 stars. If there's a single object that you found there that is really super interesting, you would pass it on to another facility.
So you wouldn't modify the survey to...
Yeah, because this is a wide field survey. It's not cost effective to do sort of space telescope type zeroing in on something with this kind of beast. Except for LIGO, and I'll get back to that. That requires special effort, and I think we should do it. Okay. So this is, so we have these simulations of, this particular one is called Minion 1016. Operation simulation. We have done simulations of 10 years of observing with a certain kind of cadence. And we have a whole pile of these simulations. And this is a result of one of them, and you can plot the results in different ways. This plot shows you the median gap between revisits to the same piece of the sky within one night. And you can see that, you know, it's a third of an hour with this particular cadence. It could be twice as rapid with the rolling cadence. And so you can see that we're doing pretty well in terms of uniformity of revisit times. The other interesting thing to this community is the inter-night revisit times. How many nights is it that we go back to the same piece of the sky? And that's this distribution. You see it has to be sort of quantized because, well, Earth rotates. So that's this distribution, that's the inter-night revisit. And again, this could be more rapid because we could do the rolling cadence. So with regard to gravitational wave sources, in the first couple of years, we are actually going to have a pretty deep understanding of the sky in terms of galaxies and also in terms of transient objects. That's a nice sort of history to have if you have something that is popping off in this 100 square degree area. So this is valuable stuff in order to build up the catalog of known transients. Another issue is the median air mass. You don't want to be looking through a lot of air when you're doing precision photometry. And you would like to have, so we have a requirement that the main part of the survey have an air mass less than 1.4. And you see we were able, in this particular simulation, we were able to maintain that over the 18,000 square degrees. We suffer in the north ecliptic spur. This, by the way, this red line I should point out is the ecliptic. That's where that's where, actually back to college. That's where the asteroids live.
Can I ask why is air mass different in the galactic plane? Maybe I misunderstand something.
It's observed at a different time.
Yeah, it's observed at a different time because
okay.
it's pretty sort of hopeless. That's a good point. This is a mistake. We're not doing this. This was a bug, but we are doing that.
And that it's all observed in the first year, therefore you're going to...
Thank you. It's we want to finish this. Actually, that's not a done deal, but that's what this
This particular...
thank you. Yeah. And then the south contains the southern cap contains interesting things like the Magellanic Clouds and whatnot. It's our duty to cover them in the time domain. And so it's a wide, fast, deep survey of 37 billion objects in space and time. Each patch will be visited over 800 times. That particular simulation was, I think, 816. 30 trillion measurements, all on spinning disk. And so we are obligated to serve this to the community in some way. There's something called level 1, which are these transients. And so there will be and transmitted to the community within 60 seconds of observation. Yeah.
What's the content of that alert for someone who doesn't know?
Position, postage stamp, all of the time history of that object, if it was an object, and all previous imaging of it. Quite a lot of information. And color information, if we have it, we probably will. A fair fraction of those are going, some of those are going to be false alarms. And it's up to the data brokers to distinguish, disambiguate that. But as I'll mention in a second, a lot of them are real objects. So this forms a significant background for following a gravitational wave lens.
So do you have several criteria to determine what the transient is?
So that's up to the broker. We have been asked by the astronomy community, please do not classify objects. It's our job to do that. So as a project, we're not doing that. We're going to give the astronomy community enough information here to do that. And they are hopefully going to step forward and do that. Only one group has done that so far, called Antares, but we need more brokers, particularly for this project. No one has stepped forward to try to use this data for gravitational wave purposes. So there'll be a catalog, level 2, this is the static sky, the catalog of 37 billion objects, 20 billion galaxies, 17 billion stars, lots of data. Deep co-added images going to 27th magnitude. And then at level 3, there are services available to the astronomy community for computing on this data set. We're going to make that available too. But a lot of the computing is going to have to be done by individual groups.
We have an automatic way to associate the transients with the galaxies. I mean,
Yes.
connecting level 1 and 2.
Yes,
Okay.
absolutely. In fact, that's going to be part of the data release. Yeah. So this transient exists in galaxy number such and such. Yeah. And we'll have the redshift of the galaxy also. So it's a new sky. There are various, I don't have time to go through all the science applications. This is dark matter and dark energy. This is looking at streams of stars, running the movie of the assembly of our galaxy backwards to see what happened. Because you can go out to 100 kiloparsecs, more than that, several hundred kiloparsecs, looking for star streams by astrometric motion of stars. Sort of cool. And then something that we're interested in here in this room is the moving objects. I think we need to be interested in this for a reason I'll tell you. And this is finding near-Earth asteroids. These are just a few of the 100 or so science applications that are in the science book. So it opens the time domain window, the faint time domain. And so very briefly, you know about dark energy. I have to go through this. You want to look at galaxies as they evolve through cosmic time, and you want to measure the position and shape of about 4 billion of them to high precision, and that's what we do with dark energy. And we can throw that data at your favorite theory, and this is the fractional error in two quantities that we can very easily measure. If you combine weak lensing LSSD probes with variant acoustic probes with Planck, you can measure the growth of structure, the growth of dark matter over densities through cosmic time, function of redshift, and you can measure the geometry of the universe. Those two things, you can throw your theory at this and see where it lands. Fun. And so you can check off the boxes of the different types of probes that dark energy the experiment has, and there are lots of independent probes. So it's in some sense maximally sensitive to new physics. Okay, more interesting to this group. Here's a cut that a student of mine just last week made on a simulation of LSST using a particular code to find photometric redshifts. But it's a bright cut on magnitudes. It gives you an idea of the redshift distribution of galaxies that are relatively bright compared to the limits that I just told you about. So this is like 21st magnitude. And some of those guys live out of redshift 1, but most of them live around redshift 1.5 or so. And you can see that that's the redshift distribution. Well, these are the redshift distributions of these various different cuts. We will have virtually 100% coverage of all the galaxies inside of the interesting volume that gravitational wave detectors will have up until 2025 and beyond, I think. this is no indication of the accuracy of our photometric redshifts. Those are very narrow little bands through here. This is just the overall broad redshift distribution of these kind of cuts in the R band. Lots of galaxies. Here's a better understanding of the accuracy of the photometric redshift. This is at year 2 on the left. Photometric redshift versus the true redshift in a simulation. Yeah, you can sort of get it pretty much right. A few outliers, but by 10 years, it's much improved. And we are actually making a lot of progress on the low redshift end of this right now, because those galaxies are actually morphologically resolved with LSST, and that information had not been used in this plot. And so if you know what the shape of the galaxy is, and you know what the surface brightness profile is, you can say a lot more about the likely photometric redshift. So we're making some progress there.
So before you go on,
Yeah.
maybe this is obvious, but what are the branching structures that come off of this?
Oh, that's a good question. Those are regions between the when I showed you those filter shapes, there are regions sort of in between the filters. We tried to avoid that, but didn't fully successfully. And so if you have the characteristic wavelength of the spectrum of a galaxy, like the Balmer break, moving through that wavelength range, there's a degeneracy. So more interesting to us in this audience is the alert rate. In 10 minutes time, LSST will issue about anywhere between 3,000 and 20,000 alerts at 5 sigma. So if you give us your cell phone numbers, the 20,000 includes a lot of the near the asteroids, and I'm going to talk more tomorrow about how we might be able to deal with them and get rid of them. So I went to Lynn Jones a couple of weeks ago and said, Lynn, I'm going to a conference where we're going to treat asteroids as vermin. And she's the asteroid person on our team. I said, okay, fine. So I'll do some calculations on vermin. And so I'm going to show you some of her results tomorrow.
Yeah. So when Faye talks about, shallow and deep, exposures for each of the, different classes of facilities that you talked about. But so this is the
main survey.
Right. But so is your software ready to handle, deep exposures and the increased number of sources that you'll find if you integrate for half?
Yeah, that's why we've sized the data management system to be so insanely large. We've sized it to do 10 million alerts per night.
Okay.
And I personally think we're not going to get near that. If we do our homework, and ZTF is going to be a real important voyage before ours, we're going to learn a lot from ZTF, and we've already learned a lot from PTF. And, I don't think we're going to get up to a 10 million a night, maybe 1 million. I think our data is going to be reasonably clean compared to what you've seen before. But many of these objects are going to be moving, and as I mentioned tomorrow, we're going to try to. I have a suggestion of how to remove them. But several thousand will be flaring objects at burst, perhaps new things, which is sort of exciting. Yeah.
Have you thought of crowdsourcing?
Oh yeah, that's so biased. It's so hard to manage. Yeah. Yeah. We should chat about EPO, but it's a touchy issue. But any kind of follow-up requires high purity samples. So what we need now, this is getting back to the event broker issue, we need people to step forward and get involved in event classification, because that's not our job. And this classification has to happen fast. Yeah.
To what fraction of these do you think we will have redshift? Sorry, redshift, but generally speaking, some information about the spectrum.
Yeah, well, as I mentioned, with these 6 filters, we'll have a 4-person's spectrograph, and so we'll have photometric redshifts accurate to 0.031 plus Z.
Okay.
0.031 plus Z.
How far apart in time are the different filters?
Oh, that's a good question. It really hurts to change them rapidly. I wish we could. So they'll be an hour apart, generally speaking. Yeah.
Along with photometric redshift issue for galaxies, how quickly will the photometry be available for galaxies? Because you mentioned the galaxy catalog, I imagine that's just position.
So that, the photometry, that catalog of galaxies gets updated every 6 months.
Okay.
However, if there's an alert associated with one of those, or even if that galaxy is near where there was an
Right.
alert, that information gets sent out with the alert.
Okay.
So I don't think this group should be concerned about not getting that information.
When you say that there's, you know, each alert contains all of the history of it, you know, of a
All
given...
previous visits.
Right. So is that really retransmitted with every single...
Yeah, and that's part of, exactly, and that actually is part of this huge rate. There's a bookkeeping issue here, and so part of the project has been advertising that we're going to have gazillions of transients every night, and actually many of those we already knew about because it was issued before. It was a known thing, but we reissued that.
So is there any savings that would be possible by just sending a delta for each?
Yeah, and that's a service that you can subscribe to.
Okay. Obviously, you have to bookkeep which ones you...
Yeah. So this gets to a touchy issue in the project. That is, this is an automated discovery machine. It is a data exploration opportunity. We are going to almost certainly discover something unexpected that we didn't design the facility to discover. And we want to maximize those chances. We don't want to do anything in our project as we're building it now to paint out parts of that scientific discovery space. And besides, we need it anyway because this is required for automated data quality assessment, which is something that we have told ourselves we're going to do anyway. So there's going to be quite a lot of this, and it feeds in a positive way to the alerts. This is just a diagram that came from Rao et al. In 2009. Sri likes to show this of the unexplored part of the luminosity time space. So this is bright guys are up here, GRB apropos, and this goes from 0.01 days out to 100 days, and this is unexplored. And I'll bet you that there's stuff there. So this is something that I mentioned earlier today. There's an opportunity to co-observe with other facilities, including not only LIGO and other gravitational wave facilities, but also radio telescopes. And this is a transient radio sky, optical sky chart. So this is the radio, what you're looking at is the radio sky. So this is in one millisecond, the sensitivity in Janskys here. In 1 day, the sensitivity in microjanskys over here. And then this is the field of view. And here are all these different facilities, but you see SKA coming up soon on the timescale of gravitational wave events. And this is where LSST lies in the optical, in terms of a flat spectrum optic. So it's right in a sweet spot up around half a microjansky per day sensitivity. So we'll have, and somebody pointed this out in the talk earlier, I forgot who, there's really a lot of synergy between the radio light curve and the near infrared and optical light curves. Here's a fun thing that you can do. So you look at the Milky Way or the Magellanic Clouds, and you keep taking images. This is one of the projects that's going to use up that 2%. And you keep taking images, and suppose the events behind this September 2015 discovery are not uncommon at some level. That means that there might be a class of black holes that are out around 20 to 30 solar masses out there. And so they'll be in our galaxy. They may actually be all of the dark matter for all we know. No one's proven it can't be. And if it is, there will be lots of interesting microlensing events. So those guys will truck along in between us on Earth and the Magellanic Clouds, or the center of the galaxy, and cause these long-lived events. This is like a year or half a year. And that's a fun project. And then people have done work on trying to determine how how well it can be done, and it looks like it's a really viable project. So this is sort of the Macho project, this range of masses. Yeah.
That's what I was going to ask. I can't remember see the plot. So what is the mass range? Because there has been some.
Yeah, so the mass range of this is above about 20 solar masses. And this whole range over here is being debated.
Sorry, you mean, sorry.
So black holes of
Yeah.
larger than 20 solar masses.
But that's what you'll be sensitive to with
Yes.
LSST?
Yes.
Okay, so nothing below that.
Yeah, we're sensitive to that, but it's been excluded by Macho.
Because I think that there's recent papers too that say this 30 solar mass gap isn't real and it's probably constrained to 4%.
So we'll find nothing.
Well, not necessarily. I have my own opinion.
Yeah, so
wanted to
we
know
should
if
look.
yeah, I think you should. I wanted to know if you, but you are sensitive to lower masses.
Yeah, yeah.
So
And,
you cover the same.
this is not a TOO. This comes for free.
Yeah.
This comes with the ordinary cadence.
Good, okay.
Yeah. Yeah, it's a fun project. Much time do I have? Anyway. So there's some additional services that we're going to offer the community which are of importance to us in this audience. And one of them is the pre-covering service, the force photometry. Suppose you find something interesting. Suppose there's some interesting event at some place in the sky. It's either found with an X-ray satellite, LIGO, maybe even LSST. It's found. We offer a service where you can go back over all previous observations, and even though the thing wasn't found and wasn't reported, we go back to that imaging data and photometer that area anyway. And so it's called forced photometry, in order to get real honest-to-God limits, flux limits, that can be compared with models. And then on request, we can do this for a number of positions over all of the imaging overlapping that position. And this information would be available in less than a day to the community. So that's useful for classifying things. Anyway, I mentioned the alert generation. And then there's this limited subscription service. We will actually filter events if you want us to, although it's not really our job to classify. There's be no classification, but we can filter events based on various parameters and give that sub-catalog to you if you would like to have that. But the bottom bullet is the bottom line. Mainly, everything that this group here in this room cares about is going to require a sophisticated event broker of some sort. Classification engines, cross-match capabilities, etc. with other catalogs. And needless to say, this is the first time we've had the opportunity or the luxury of going backwards in time. Other previous experiments discover something and then hand it off to something else to look forwards in time. We can go back in time. We find something and then we go back and look at that same piece of the sky in previous data. This could be used as a Bayesian prior for classification post-alert. It can be treated as part of the light curve. Suppose we went back and saw the thing coming up from 27th magnitude up to 24th, and suddenly it's going to go up to 20th tomorrow. And we can catch interesting objects on their way up and issue pre-alerts. So fun. So this is meant to be the scary slide. This is a calculation that was first done by Steve Ridgway, and Lynn Jones and I improved it last week. This is the number of transient variable objects that are actually real things that have been detected, not false alarms. But these are real things that are expected to happen of different types as a function of survey year. This is during an 8-hour observing night. This is per day, but this is during an 8-hour observing night, typical night, integrated over seasons. This is not Masters in Business Administration. These are main belt asteroids. That should scare you. This is a huge number every 8 hours. These are cataclysmic variables. GRBs are a subclass of this. Stars that actually explode in a funny way that's still not understood since they're so rare are part of this. Then there are other things we know more about, like supernovae, AGNs, QSOs, and ordinary variable stars. I have to watch what audience I say this to. Variable stars. And you add them up and you start getting up to those big numbers that I told you about. But the message here is that if you thought that it was safe to go back into the water after a couple of years, it still isn't.
So just if I'm interpreting this correctly, you're basically saying that after 2.5 years, you've seen all the variable stars you're going to find?
Yeah, if you believe this, yes.
Okay.
Yeah.
But
they've been classified, so they're known
asteroids
objects. So even though they're still part of the alert stream, they're old hat.
Sure.
So.
But you're going to be detecting new asteroids.
Yeah,
till the end of time.
Tomorrow I'll talk about how a scheme to retire this risk. So
what is this dashed diagonal line?
That's a mistake. That was in the Ridgway 2015 paper where I think that he got the inverse of one of the parameters. And so anyway, that was, if you read the paper, that was the original main belt asteroid rate, and so we went around telling the community, oh, well, you just have to wait a couple of years and it won't be a problem. That's no longer true. And so somebody showed this earlier. I think this may actually be the same pile of Frank, so it's got to be real.
But there was no needle here. I thought that there was needle in the other.
Yeah, well, there it is.
But your needle is smaller.
Yeah,
Well, that's assumed. Anyway, so this is the job of the automated. This is the job of the classification broker, is to understand, is actually to classify all this stuff so that you can then have a clean catalog of those things. And so just in closing, there are all sorts of meetings and community forums and white papers and roadmaps that have come out in the last year or so that you can Google. You can go to community.lsst.org and find out a lot of discussion. There is a recent white paper that's about to get submitted to the archive called Science-Driven Optimization of the Observing Strategy. And there are all sorts of opportunities to get involved. Mainly, there's something called this is sort of cool. You might want to do this. So I mentioned these operation simulations that we're doing, and we're doing lots of them under different scenarios. There's something called the MAF, which is a software package that allows you to go in and it's called the Metrics Analysis Framework software package. And in that software, you can define what you think is the best metric of success for your particular science program. And then run it on the operation simulator and see how well you did. And so that's sort of cool. A lot of people are doing this. I'll upload this so you can look at it. You're not expected to read this, but there's just tons of different sources of information about LSST. And there are 10 LSST science collaborations, each of which has a piece of astrophysics space. The two that concern us in this room probably are the Transient Science Collaboration and, believe it or not, the Near Earth Object, the Solar System Science Collaboration, because that's the largest background source for this. So just in closing, in the subject of this meeting, the whole mission, therefore, is to somehow leverage the known sky, use the LSST data to leverage the known sky, because there's going to be a lot known about the sky after a couple of years with the LSST data. And then proceed on to do a fast survey of gravitational wave event area, 90%. So here's the TOO, target of opportunity goal, would be to search for the electromagnetic counterpart, assuming there is one, but should try. If it's feasible, that's to say if it's not noon, if it's visible, it's at a reasonable air mass, go there rapidly and start working on it right away. And then once you've found all the candidates, hand them off, unless there are a gazillion of them, hand them off to other facilities so they can follow up on them. the idea is to have just a few candidates. So here are the challenges. The air mass could be an issue. As I mentioned before, all the programs require air mass less than 1.4 and special dithering. So anything we do for this target of opportunity work is outside of the survey and cannot be reused. So that's why it's part of the special programs. Otherwise, well, that's what I have to say. So here's the strategy, which I'll talk at length about tomorrow. First, assess the feasibility of follow-up. Maybe it's noon here and it's not worth it. Is the object accessible at an air mass less than 2? More than 2, you get absolutely poor photometry and it's probably not worth your time. Plan on working about 3 hours or less, otherwise you're going to be into high air mass. And if feasible, go there and rapidly cover that 90% contour area. And it's how you do that I think we can leverage how you do that to retire some of these backgrounds. And that's this. The observing mode actually makes a big difference in minimizing false positives here. Confirm the candidates in a second rapid pass. You have some candidates you found in a first pass, confirm them immediately in the second rapid pass. There are multiple reasons for doing that. What you want to do in a third and the fourth pass, however, is another issue which is up for debate. I heard today reasons why that might want to be delayed by a day. And then I'll tell you tomorrow about how to eliminate most moving objects. And then announce candidates, hopefully a few of them now, with their time history to the world to follow up with spectroscopic and other machines. And each one of these candidates will have a lot of, as I mentioned, a lot of color information, a lot of history information behind it. And then hand them off to other facilities. So asterisk here means that it's not our job, we cannot do this. It's up to some event broker, gravitational wave event data broker to do this analysis.
So when you say it has a lot of color information, does that mean that each field will just go through the whole band?
Yeah, I'll mention that tomorrow, but I think it would make sense to have to actually do it in many filters. Yeah. Yes. It can be done inside of a few hours, I think.
But your regular mode, I missed that.
So the regular mode would do this anyway, but it won't actually rapidly cover an area. The regular mode is you go to a piece of the sky and you take a pair of, say, 15-second exposures. By the way, we're still trying to decide if it's going to be a pair of 15-second exposures or one 30-second exposure, and then differenced against some kind of archival image of that sky. Anyway, you take your pictures, maybe a couple of them, and then you slew to a new area, but you just dither back and forth in X and Y when you do this. And also rotate the camera in between. That's required for weak lensing, for chopping. So this kind of observing that I'm going to advocate tomorrow is not it doesn't fit with the main survey, and it cannot be used for the main survey.
But what filter will you use for your main survey?
All of them. All of them.
Like in 15 seconds, you don't do 5 filters, do you?
No.
Hour or something.
No. Every hour or two we'll change filters. Yeah.
And then you go back to the same
Yeah.
place?
Yes. Yeah, so we return, in the main survey, the Wide Fast Deep survey, we return to the same place every hour or maybe every half hour.
With a different filter?
Sometimes. Sometimes. It's asynchronous. Anyway, yeah, question?
I might consider, if you're able to follow up a LIGO source on the first night, just using a single band, because at early times, I think that the, additional, sampling in time would be more useful than additional.
So tomorrow I'm going to make the assumption that the 90% air area is 100 square degrees. And I'm going to show you that it's possible to do in 5 filters. Multiple times in less than 6 hours.
Yeah, but that's an entire, is that assuming you devote?
Where it's 10 square degrees, then you're free to do a whole lot of things.
Right. I mean,
but you still have this huge background transient sources stuff.
Right.
And the only way you're going to retire that is to get color information.
Well, but that's just what I'm saying. If you're doing this, if you may have a mix of follow-up strategies where
Yes.
you have one choice of cadence and filters for the first night, and
Exactly.
a very different choice of
Good
filters and
point,
cadences
and I
for
think
the
I
following
think you're
nights.
right. I think we have to be a little bit more
Yeah.
complicated. A simple example that I'm going to present. Yeah. Anyway. This is just to scare you again. So this is the false positives background.
Is that as bad, like, say, are most of the asteroids in the ecliptic and most of the...
Yeah, so I should have
galactic
mentioned, it's a
plane?
very good point. So by far, I'll show you something tomorrow on this. By far, the majority of the asteroids are within 20 degrees of the ecliptic. And so if you get outside of that, it goes down by an order of magnitude. And it becomes a sort of a minor irritant. Also, they don't tend to line up on galaxies, at least not for very long. They move typically 10 to 15 arc seconds per hour at the asteroid level.
Visits in the same position, they are not there.
Say again?
If you have multiple visits, they don't show up at the same position.
Yeah, so that's the reason. So tomorrow we're going to emphasize the strategy where you have multiple visits to the same piece of the sky during one night, or certainly between two nights.
So these are all going to be parts of the sky that have been imaged every couple days anyway.
Anyway,
so
yeah.
So it's only.
So you know the galaxies,
and
you know the stars.
You generally will know the moving visible objects.
No.
No.
That's why there's 10,000 an hour.
No. Okay.
These
Well,
are
let
new
me-
ones every single night. These are new ones that you didn't know about. The ones that you did know about
Okay,
have been
fine.
retired and aren't shown here.
Like you say, the fact that the probability that they line up with some previously known galaxy is.
Yeah, that's part of the filter. But you only get to supply that, you only get to apply that filter after the fact. You sort of like to know right away.
So
Question.
if we use the color information,
Yes.
how does it help significantly reduce the contamination from the
Yeah, because it allows you to classify all of these things in a much more robust way.
and asteroid?
Asteroids have color classes. It's a little more complicated discussion. Maybe we can have that tomorrow. There are 5 color classes. Anyway, yeah.
So, getting rid of solar system objects is one thing that goes into the thinking for like the minimum cadence for ZTF follow-up of
Right.
LIGO triggers. So, given that you're going much deeper, what is the sort of what is the minimum practical cadence to separate out, to make the contamination due to solar system objects?
I'll show you tomorrow. It's well within our capability. If we return to the same area in an hour, we can do it very easily. And if it's longer, then of course it's better. However, the longer you wait, the higher the probability that another asteroid is moved into.
Right, but what I'm concerned about is that if the exposure time's too short, then you won't be able to tell it's an asteroid because it will still be in the same place. So what I'm asking is, what is the
You mean
shortest?
the time between exposures is too short?
Yes.
Yes, exactly. So that's why I advocate covering the sky multiple times in one night.
Right.
And actually in multiple filters. If it could be done, we should simply do it. And 100 square degrees is achievable. Anyway, these are the sources of support that mainly that we're getting these days, in addition to Bill Gates and Charles Simonyi earlier on. NSF is the lead agency. It's around 700 million. Office of Science is 165, and then there's something like 40 million a year operations.
How much is it? How much is private?
About 50.
50 million.
Yeah.
Okay.
You're wondering why we invited you here. Yes. Yeah, something like 50. Okay, so that's it, I think. Thank you.
0.03 1 plus E for the redshift. So for these LIGO targets, we obviously would prefer to do a cut on very low redshift
Yeah.
galaxies. So our ability to have like a cut on the very nearby. So is it actually, does that uncertainty
So-
actually extend all the way to Z equals Z?
Yes and no. The vanilla photometric redshift that relies only on color information gets poorer down around a redshift of less than 0.1. However, and I mentioned this in passing, I have a student that's making a lot of progress on using morphology information mixed in with this color information. And he's able to get even better accuracy at lower redshift where the galaxies are actually resolved well enough to say that this is a spiral or it's an elliptical, and therefore that cuts down on the number of spectral templates that we have to use in the photometric matching for redshifts.
So ideally, you would, if you were interested in LIGO, you want to click the box where those were sort of the galaxies,
Yeah.
transients in those types of galaxies are the ones
You
that are
could-
being fed to you.
It's a delightful game. You can you can make cuts like that of the data after the broker, or maybe that's the broker's job then, to make cuts on just known galaxies. That assumes, maybe this is reasonable, that assumes that gravitational wave sources live in galaxies. I don't know. I just work here. Maybe. It's likely.
Or, I guess also, like, how will you, if you have a transient that, I mean, will it literally have to overlap the galaxy, or will there be some sort of probabilistic algorithm with respect to how close it is?
That's a good suggestion. I think there should be.
I can say that in other fields like the supernova, we definitely think about probabilistic
Yeah.
galactic process.
Very useful.
I guess along those lines, so you mentioned whenever a transient's detected, there might be information about a nearby galaxy in that
Yeah.
vicinity. Will there be a way to kind of query, all the galaxies within,
Yes. That's one of the query.
Okay.
I went through that slide too fast. That's one of the things that you can ask the data center to deliver to you.
Okay.
It may take an hour.
Right.
That's
You
up,
have the-
that's up for discussion still.
Okay.
We haven't decided.
So they do the angular distance and with geometry, you got all the nearby galaxies and do the
Right.
probabilities.
Exactly.
I wanted to ask more
Linus.
about the filters. So what do you see as the kind of basic thing? You use your favorite filter, which is maybe R or something, and use that routinely, and then every
No, we
few
go through
hours
all-
you swap to another?
We
or-
go through all of our filters, spending a fair amount of time on each one. Actually, more time is spent on the redder filters because it's a little more challenging because the sky is red. So you have a background problem, a foreground problem. But yeah, we spend time on each one of our filters.
Every night? Or, I was trying to understand
Except for the
how
U
that-
filter, which is out of the camera, except for special occasions.
And so the sequence is,
G-R-I-Z-Y, G-R-I-Z-Y, G-R-I-Z-Y. But we're not married to that. If the scientific community thinks we should do something different, we still can do that. It's just, we have an example cadence that seems to work.
I think that the quote of this conference should be that the sky is red.
The sky is red, and it's falling. Asteroids are about to hit us.
Okay, thank you very much, Tony.
Yeah.